So then we're going to just leave it in this simple form in order to plug it into our calculator, and we continue on with plugging in values. So we just plugged in this guy for our first equation. We then just take this guy and plug it in for our second equation. We plug this number in for t. And we plug in 1.52 for x. It'll be cubed here, squared here, and then just 1.52, and then d. That was our second equation. We move on to our third. And our fourth. All right, so we have 4 separate equations that represent these 4 points that we were just given, and we're going to use them to solve for A, B, and C, and we're not going to expand them. We're just going to leave them like that, and we're going to plug it into our systems of equations in our calculator. So you go to Menu, Algebra, Systems of Linear Equations. We have 4 equations, and I'm going to do A, B, C, and D. And you type these all in exactly as you see them, which takes time. So go ahead and plug these all in. I'll pause the video for you right here and plug them in and double check that you got the same as me. Okay, so when we plug this all in, notice I left it all not expanded, right? I just left it as 0.723 cubed. And I typed it all in exactly like this. My A is bolded. I think it's because since this is my scratch pad, I have something saved on here, and I don't know what, but it gives me the right answer. So I'm not super concerned about it. So I press enter on this guy once I get all the way there, and I get these massive long numbers. You can always scroll up and move from side to side and scroll back through all of those answers. Remember that it says our coefficients need to be to 3 significant figures. So that's what I'm going to do is I'm just going to take the 3 of the significant figures. So A is about this first number, negative 0.00342. B is about 0.251. C is about comma, so then this is our new number, 1.0, and then since 3 is our third significant figure, 7 will tell us to round up to 4, and then D is about, and that's here, negative 0.265, since the number after it is 2, we keep it at 5, so negative 0.265. Those are our 3 coefficients, and we can put it all together into one big equation because we want to find the cubic model. So we don't get points if we just leave it as A, B, C, and D. We need to actually have the equation written out. T as a function of D is equal to negative 0.00342 D cubed plus. And there you have it, our final equation. It then asks you to use this model to predict other things. So I'm going to go ahead and immediately plug this model into my graphing calculator. I will also be asking you to give me some of these answers. So plugging them into your calculator right now is going to be the best way to go. We get a function that looks like this. So I go to zoom standard first, and then I might do zoom fit afterwards. It looks like a parabola, but I know that this is a cubic function. So if I see a minimum here, I know, because with cubics, that they need to have a maximum, right? This is why we study the behaviors of these functions before we start talking about the model, is that if I see a minimum and I know that this is a cubic because it's raised to the third power, I know that somewhere in here, there's a maximum. And so I just need to go and find it. So sometimes your zoom fit doesn't help you really all that much. And here we are with these values. I'm going to go ahead and erase old points that I found earlier. They're connected to the last graph. And I want to see, okay, when Jupiter is 5.20 astronomical units, well, that's my distance, right? What does this model predict is the orbital period? So T, which is my orbital period, is question mark. Notice the prepare step here, right? I underline the things that I'm given and assign them to a variable. And if I want to find the orbital period, I have a variable associated with that, T. So I say T equals question mark. So this is where I'm writing down all of my work. So I'm going to plug that in for D. In other words, I'm going to find out what y is when x is equal to this. So this is our super easy. We just trace it and we do 5.20, enter, and it tells us the answer is 11.4. So 11 t of 5.20, which you could have plugged it in for d and cubed it, squared it, and all of that, but that's a ton of work when you could just plug it into your calculator. We get 11.4 years. So it takes 11.4 Earth years for it to actually do one whole orbit around the sun, which means their 1 year is equivalent to our 11.4 years. It says that the true value is 11.9. Calculate the percent error in the model's prediction. This is a flashback, a throwback to something that we've done in previous units. So remember that your formula for percentage error is in your formula packet. We've already learned how to do this, so I would like for you to see if you can do it on your own. 11.9 is our true value. In other words, E for exact. 11.9 is our exact value. Our model predicted the orbital time, so it was approximated at 11.4. The formula for percentage error is this, where you subtract the 2 in the numerator and then divide by your exact value. So you should have 11.9 minus 11.4 all over 11.9, our exact value in the denominator. And we get approximately 4.20%. So our model has an error of 4.2%, which is a significant error. All right, according to this model, what is the maximum possible orbital period of a planet in the solar system? Try to do this one completely on your own. Some things that I would tell you to do in order to start with this problem. Maximum. Anytime you see the word maximum, minimist, largest, smallest, that means we want the vertex. With cubics, we have 2 vertices, a maximum and a minimum. So then obviously with this guy, we want the maximum. We want the maximum possible orbital period, which means we're looking for the t, which is really the y value of this point, right? That is the thing that we care about when we're talking about the vertex. So when we go in, menu, 6 for analyze graph, 3 for maximum, we go in and find that maximum. We get an answer of 50.9252. Now, this is our distance away from the sun, and this is our orbital period. So remember what all of that means in regards to your categorization of the variables. Since it's asking for the orbital period, that means that our answer is this number right here. If you just give the value or the point back, it's not going to be correct. So 252 years would be the orbital period, the maximum orbital period using this model. Great job.